Okay, so we're gonna do set equivalence here, and we're gonna do it the right way. So in the other video, it's not true. This is the true statement, and let's prove the true statement. So again, I need to show that if there's an element in this left-hand set, then it's in the right-hand set, and if there's an element in this set, then I gotta show it's in the other one, and then I've shown that the sets are indeed equal. So let X be contained in this set right here. Right? If X is in here, then this is an intersection. So we have it that X is in R and X must be in this union. And then now X being in R and X in S union T means that X is for sure in R and X is either in S or X is in T. So that means that, that means that this is going to split, right? X is for sure in R, and X could be in S. Okay, X is in S, right? Then that means that X is in R intersect S, which would mean that X is in here, and then that means that it's only in, and then this is a union, so this would imply X is in this union. But that's if X is in S. But if X is in this, then it's either in S or it's in T. So the other thing you should just say is that X must be in R, and then if X is in T, then that means that X is in both R and T. So X is in R intersect T, which would mean that X again is in the right-hand side, and you're done. I like these set proofs because they're kind of just like I find them to be very straightforward. And that's one direction. Now the other way is to say, right, and then let X be in the right-hand side, and you want to show that it's guaranteed to be in the left-hand side, and then you're done. So if X is in here, this immediately means that X is either in R intersect R intersect S, or X is in R intersect T. So say, right, it's either in one of these, X is in R intersect S. Then that means that X is in R and X is in S. But if it's in both of these things, then that means that we have X in S union T. But then that means that you have X in R and X in S union T, so this whole thing then implies X is contained in R. X is contained in R intersect S union T. Because it's in R, and then we just showed that it's in S, so then that means that it's in S union T, so then X is in there. But that's if X is in this piece, but X could be over here in this one. So say, right, X is in R intersect T. Well then, X is in R again for sure, and X is in T. But this part implies that X must be in S union T. And then since it's in S union T and it's in R, X is in R intersect S union T. And now I've shown that if I let X be in here, then it's in here. And if I let X be in here, then it's in here. And I've shown the set equivalence in both directions.